Hi everyone, how are you doing today? Hmm. So today we're going to be doing something different a bit. We're going to be having something called study sessions with Mo. So yes, hello to everyone on LinkedIn. So we're going to be having what we call study sessions with Mo, and these sessions are basically just to prepare for various interviews or just to have general knowledge about computer science. Keep up to date. So yeah. So I'm going to be sharing my screen, and you're going to be seeing some resources I'm using. I'm going to be using resources like Geeks for Geeks, resources like YouTube and LeetCode and the solution section, and maybe some educative.io because it's a very, very good platform. So I'm going to share my screen real quick, and you can follow along. So yeah, I'm excited. Okay, is anybody watching? Not yet. Not yet. So let's see. Share screen. Entire screen. Screen one. Okay. That looks interesting. So right now, let's study about what's breadth first search and depth first search is first of all. Let's look at that together. As I do that, I'm gonna move the stream to another page. So let's check it out. So what is breadth first search? Or what is a tree? So I was studying about this recently, and a tree is basically something that has nodes in it. I'm still learning about it, but a tree has nodes in it. Let's look at it together. So what is a tree? CS, computer science. So it has a hierarchical tree structure with a set of connected nodes. So yes, that was what I was trying to say. So when we look at this picture, right, we see different things on it. So we see a node over here, then we see another node, and we see another node, and we see that they are all connected. So a tree basically has a node with other connected nodes with it, right? Just to make it in simple terms. Then let's talk about breadth first search and depth first search. But before we get there, I was watching a video about how there are different types of trees. There are binary trees. So binary trees basically have two nodes connected to them. So when it comes to trees, we can also look at the different ways to traverse a tree. And so when you're talking about tree traversal, you're talking about how to move through different different nodes in the tree. So we have breadth first search and we have depth first search. Okay, so we have breadth first search and depth first search. So breadth first search. Okay, so there are different ways to traverse a node in a tree. There's breadth first search and depth first search. Let's cancel some of these over here. So, oh, sorry, I clicked on something. Okay, so a tree is traversed in two ways. So we see that a tree can be traversed using the breadth first search or the level order traversal, and it can also be traversed using the depth first search, which has to do with the different ways of traversing through it. Like, so breadth first search. When you think about breadth, what comes to your mind? I think about like width, income, instead of height. So when we talk about breadth, I'm talking about width. So when we look at this over here, we see a tree over here. And what it's telling us here is that we go from 0 and then we go over to 1, then to 2, then to 3, right? So then we now go over to 4, then to 5, then to 6, then to 7. So we see here that it's going breadthways. So it's going level by level. It's going level by level and it's going horizontally, not vertically. So we're moving from here, down here, all the way down. And so the numbers are going to be 0, move down, 1, move over, 2, move again, 3, we move down, 4, 5, 6, 7. Now let's talk about depth first search. So when I talk about depth, what comes to my mind? What comes to your mind? Right? You can tell me in the chat if you're watching. So when we talk about depth first search, I'm talking about. I can expand the picture. So depth first search, I'm talking about like going downwards, right? So depth, meaning down. So over here we have 0. We go down to 1. Then we go down to 4, right? Then we go over to 5. Then we go over to 2. We now go down again 6. So basically, in breadth first search is going row by row. In depth first search is going like an entire tree first, then another one. So it's going down, and it makes sure that it touches all the nodes that are there. So we have 0, 1, 4, then 5, then 0, 2, 6, then 3, 7. Okay, so depth first search is different from breadth first search. Fun fact: most of the interviews I've been to, they usually ask about depth first search, so it's interesting. Yeah. Now let's keep going. So, what is breadth first search? So, breadth first search is a graph traversal algorithm that starts traversing the graph from the root node and explores all the neighboring nodes at the present depth prior to moving to other nodes. So, like we said before, right, it keeps on going down. Uh, it keeps on going, level by level. So, it starts with the first level, layer 1, 0. Then it goes to the second level, layer 1, which is 1, 2, 3. Then it goes to the third level, which is 4, 5, 6, 7. Okay, now let's keep going. So, how does breadth first search traversal work? How does breadth first search traversal work? So, breadth first search explores all neighboring nodes at the present depth prior to moving to the nodes at the next step level. So, in simple terms, it's basically saying that when it comes to breadth first search, we first go to the first level, right? Looks at all the nodes that are here, then now goes to the next level, as opposed to depth first search. So we start at the root node, then we add it to a queue. Okay. While the queue is not empty, dequeue a node and visit it. Then unqueue all the children into the queue. I've been learning about stacks and queues. You might not have read about it before, but there's something called stacks and queues. And I'm going to use educative.io to actually explain this. So educative.io has really been helpful to me in learning data structures and algorithms. I'm still growing, I'm still learning, but I'll tell you that they are very good at explaining things and giving practical examples that will be likely replicated in your interviews. Like, I've been to a lot of programming interviews and I've seen that the things they teach here, it's actually represented well. So one thing I wanted us to look at is stacks and queues. I don't know if they have it separately, but there's stacks, right? Stacks is mostly like a last in last in first out kind of deal. So when I say that, let me show you what I mean. So imagine you have a set of pancakes, right? The reason I'm explaining this is because it's important when dealing with bread first search and depth first search. So imagine you have a set of pancakes, right? And you are basically making a pancake castle, right? You are laying it on top of each other. And so you put the first one, let's say this is it, right? You put the first one, you put the second one, you put the third one. Now the last one that's in right now is the third one. But when you now want to remove it, it's going to be the first one out. So that's what it's talking about when it talks about last in, first out. But the queue is opposite to this, right? The queue is last in, last out. Okay, it's not the same thing. It's last in, last out. I don't know if they have it here. Maybe in bread first search they would, but I can't see it. So I'm just going to give us a practical example in this scenario. So, for example, in a queue, let's say that you're actually standing in a queue. Let's say that you're standing on a line. You want to buy coffee or something like that, right? What happens? So, different people are lining up, right? The first person comes to the line. Let's say um, person A comes to the line, then person B, then person C. Okay? So, person A is in the front row. Now, who is going to be attended to first? Person A or person C? So it's likely going to be person A, right? And what's going to happen is that they're going to ask person A, "Oh, what do you want for coffee?" And they'll answer when the person pays, right? He or she pays. He will then leave the line, and then the next person will come forward. So we see that it's in a last in, last out. So if you come last, you'll be served last. So in the same way, that's how it works with queues, and we implement queues when we are working on breadth first search. So when it talks about DQ and Q means add to the queue, DQ means remove from the queue, so pop. So this approach ensures that all nodes are visited level by level, moving horizontally across the tree before moving to the next level. And in this way, breadth first search explores the nodes in a breadth first manner, making it useful for tasks like finding the shortest path in unweighted graphs or trees. So breadth first search can be used for things like finding the shortest paths in trees or graphs. Now let's look at depth first search. So depth first search is quite interesting. I think I might open up a whiteboard here so that we can also be drawing as we are learning about everything. Let me see. Is there a background audio? I'll check if there is. I don't want y'all to feel uncomfortable, like, how what's I see so loud. But yes, so let's continue working on this in the meantime. So when it comes to depth first search, so depth first search is a technique used for traversing trees or graphs. Okay, so let's say that you want to move through all the nodes in a tree, right? You would use either depth first search or breadth first search, but this time I'm talking about depth first search, and backtracking is used here. So in this traversal, the deepest node is visited, and then backwards to the parent node if no sibling of that node exists. And I'm going to explain this real quick. So when we talk about binary trees, we're talking about um, trees where the node has two children, a left and a right, right? So let's see if the whiteboard has loaded. Um, do I have the paper? I just want something to draw on because I wanted to just draw on something, but I can't see my tools for it. Okay, maybe another day I'll use this. Okay, I see it. It was the sharing screen that was showing. Okay, so let's say that I have a tree over here. Okay, this is my node. It looks quite interesting. So now it looks like a stick man actually. I have one here and I have another one here. So I have my node over here, right? This is stands for N, and this is my left. Oh, no. I'm drawing with my computer, so maybe next time I'll use my iPad. But yeah, I'll use my iPad next time. So this is my node, this is my left, and this is my right. Okay, so now let's talk about depth first search. Most times it's actually not like this. Most times it connects from the roots, but I don't want to spend so much time just drawing it so we don't lose track of what we're doing, right? Let's be intentional. Okay, so here it is. So this is a tree right now. This is a binary tree. It has two children, and you can have also other children too. So this is the main node where everything is connected to. And when we're going through depth first search, we have three ways of traversing. Right? We have three ways of traversing. We can go in order, post order. We can go in order traversal, pre-order traversal, or post-order traversal. And so when we talk about in-order traversal, we are traversing to the left subtree, right? Then we're visiting the node, and then we're traversing to the right subtree. So this is how it works. When we talk about in-order, this is my right, this is my left. Okay. I like just to be sure. So when we talk about in-order traversal, we're traversing to the left. So the first one is we go to the left, right? So let's say that we are trying to traverse through this. We visit the left node first. So that will be left. Then we'll visit the roots, right? The roots node, which is what everything is connected to, which will be, let's just call this N, and then we'll then go to the right node. Okay, then we'll go to the right node. That's how in order traversal works. No, yes, in order traversal. So you go to the left subtree first, then you go back to the roots, then you go back to the right subtree. And in pre-order traversal is quite similar. So in pre-order traversal, we visit the roots first, then we traverse to the left subtree, right? We traverse the left subtree, then we traverse to the right. So pre-order traversal, roots, left, right. And then post-order traversal, we go to the left subtree, then we traverse to the right subtree, and then we visit the root again. Okay, so there are differences between depth first search and breadth first search, but the major thing that I want you to consider is basically what they mean, right? Breadth, depth, vertical, breadth, horizontal. Okay, and in depth there are different ways to traverse. Then for breadth, we use queues. For depth, we use stacks to build them up. So I believe inside here I had some examples. So if you don't know, I created a study guide for data structures and algorithms as I am studying for interviews. You can check it out, look at it, tell me what you think. um so let's continue real quick. When we talk about, I have a section here specifically for trees, and I have different sections. So I spoke about initializing a tree. When in coding interviews, sometimes people want you to initialize a tree from the start yourself, and I did everything here in Python. So we can see the node class. So first of all, I'm initializing it. I think this is meant to be, yeah. I'm initializing it. So I have one that is called self.data. Then I have my left node and I have my right node. Then if you want to insert a node to a tree, here is the code to do it. And if you want to check if a value is contained in a tree, you can check it over here. So now, I solved a question recently. You're going to see this. I'm doing a 100 days data structures and algorithm challenge. Oh, hi, Michael. Thank you so much for commenting. I'm so happy. But I saw it pretty late. I wonder if you're still watching. But yeah, thank you. Yeah, you're right. So stacks provide the perfect scenario. Yes, that's true. So I was solving a question here, maximum depth of a binary tree. So, like I said before, forgive my drawing from before, but like I said before, even though the drawing is getting better. Don't worry. Next time, I'm going to bring out my inner artist. So, it says, given the root of a binary tree, return its maximum value. Okay, so given the root of a binary tree, return its maximum depth, actually. So a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest left node. So over here, this is a binary tree. How do I know? So I look at it, I see that it has children, right? But not just any kind of children, right? Not just 5 children, 6 children at once. It has two children each. So we have the root node over here. Then it has 2 kids to the left and to the right. And the right child has other children. So they have grandchildren. So it has one that's 15 and one that's 7. So right now, we're then going to look into how does this work. So I'm looking at the depths. So first of all, this was already a hint for me that, oh, there's this. So this is likely going to be, sorry for the notifications, this is likely going to be depth first search. So right now, I want to check for what has the longest depth. For in this example, we see we have 3 over here. And if you go down, we see we have 20, right? So we're counting level. So 3, and we go down. So that's 1 already. No, 3. This is the first level 1. Then we go down. That's 2. Then we go down again. That's 3. So over here we see that we have 3 levels, and that's the maximum depth. So we return 3. Then another one that we're looking at is example 2. So we're looking at the roots. We already have them. So we have 1, now 2. This one wasn't drawn for us, but I would guess that like it's probably, so if this is 3, 9, 20, so it just has 2. So it's probably 1, then 2. Just picture that in your mind. I'll have more visualizations later. So over here we have 2 here because 1, 2, 2 levels. So now I use a recursive approach for this. So if you don't know what recursion is basically, this is how I understand it. And you can also, if people here are experienced in data structures too, you can also put it in the chat, what you know about recursion. So recursion has more to do with calling a function on itself, right? And using that to solve the problem. So Educative has a great example on this. So let's look into recursion too, just a bit. The reason I'm branching into this is because I want us to have a solid understanding before we just get into coding, right? Because in programming interviews, they might switch the question a bit and it can show you off track. So let's check recursion. Is he here? He should be here. Probably is it under dynamic programming? Let me see. I have another good article on recursion. So I have one that I did before. Where could it be? Okay, I'm going to share it real quick. Recursion. Okay, so I have an article from Geeks to Geeks. Geeks to Geeks is an amazing resource when it comes to data structures. Like, they've done such a good job. So I have one on recursion and I have one on backtracking from Geeks to Geeks. Very useful resources. Okay, so like I said before, what is recursion? They asked, so it's when a function calls itself directly or indirectly. And depth first search uses recursion a lot. Like in your in-order, post-order, pre-order, they use recursion a lot. Recursion is an amazing technique if you want to reduce the length of your code. So that's why I use recursion. But I'm going to explain specifically why I use recursion in this approach. You can go and look at the article if you want. I can even post the links in the chat. So I'll post the links for everything I used in the comment section, and you can visit it yourself and enjoy. So let's see. And I also solving. So let me post this for you too. Do you want this study guide? I'm still improving on it, but you can have it. Still completing it. Oh, I won't have examples of recursion over here. I solved the question elimination game. Okay, so maximum depth. Let's look at it together. Now, we see that we're meant to be calculating each level. Okay, so when it comes to recursion, you need to have a base case. So what is a base case? A base case is when I want to say you set a case, but I don't see the same term. So if something is wrong with your algorithm, what happens, right? If there's a particular scenario where your algorithm cannot work, what do you do then? And so that's what the base case is here. So if there's no roots, right? If everything is zero, there are no children, there's no roots, there's nothing attached to it. Because if there's no roots, then there are no children, right? If there's no roots, just return zero. Okay? But if there is a root, what are we going to do? So what we're going to do is we're basically going to be calculating the max value of all the levels in our tree. So we start from the roots, then we go down, right? So that's why we have 1. This 1 is actually, we start from the roots, which is 1, plus we now go down, we go to the left, then we go to the right. Okay, so we get the max roots, the max values between the left and the right subtrees, and that's what we then use to calculate what is the maximum depth. Okay, and this approach is very nice, very simple, very clean. I love it actually, and I believe it's an O of N approach. But yeah, so let's look at another question from Educative. The reason I choose Educative is because I just like them. But no, not just that. I like how they explain the solution very, very well. Okay, they explain the solution very, very well. So, but this time we're going to be looking at, should we look at a breadth first solution or a depth first solution? You can put it in the chat, anyone you prefer us to use. I've done most of these ones. So let's try flatten a binary tree. Okay. But this time I'm going to be looking straight to the solution. Then we can look at other ways to solve the problem because I'm also still learning. This is for accountability and so that we can grow together. Okay. Now it says, given the root of a binary tree, the task is to flatten the tree into a linked list, including using the same tree node class. The left child pointer of each node in the linked list should always be null, and the right pointer should point to the next node in the linked list. So the reason I like this question is because You need to picture it in your mind. So sometimes you just read a question and you might feel confused initially, but as you keep on going, as you keep on solving, you feel better, right? You start to understand what's going on. You start to understand, oh, what's different, right? So let's look at it together. So the left child pointer of each node should always be null, and the right pointer should always point to the node in the linked list. Okay, and another reason why I like educative is that they draw it out for you. If I'm in a practical interview setting, I would like to draw out what I'm doing. In fact, I should probably have a book and a pen as I'm doing this. Yes, next study session, we're going to have a book and a pen. So there are different ways to solve this problem. They have already given us a hint that, oh, the right pointer should point to the next node. So let me see if I can. Can I draw here? I can't draw here, but I can draw here. So let's clean this up. Now, let's say that I have a tree over here, something like this, right? And I want to, oh gosh, which my drawing is it's so interesting, guys. So interesting. My LinkedIn viewers and YouTube. Also, if you have been watching this far and you're enjoying it, you can subscribe. Right? Okay, so let's say I have this two over here. This is a tree and I want to flatten it. So it told me something over here. It said that the left child pointer of each node in the linked list should always be null. So basically it's only going to be pointing right, and it's going to be pointing right until it is flattened. So this should point to here, and we're not having any left node. This should be right. So we can actually try it like this. So we can point this to the right, then we can point this again, so that everything would become, let's say this is B, let's say this is B, this is A, and this is C, right? If you point everything like that, so become BAC. I'm just trying to understand the question in my mind before walking into programming, because one mistake you can make is to just start coding. So let's still look at the thing. So that's how I would have done it. In this scenario, I'll probably use a kind of traversal method to do this. So like I said before, I started from the left, then I went to my root node, then I went to C. Wait, I don't want this to pass 30 minutes because we've already been here for 28 minutes. But I started from that. And if you remember what we spoke about, if I'm starting from the left to the root to the right, that is in order traversal. So I might have used in order traversal for this, but I'm then thinking about different scenarios if this is the best way to do it, right? But let's look at the solution just to check it out so I won't waste time. So far you've probably brainstormed some approaches, have an idea on how to solve this problem, which is good. So you see how they break everything down, which is very, very useful. So then I said the naive approach to flatten a binary tree into a linked list is to perform a pre-order traversal and store the visited nodes in a queue, which is an amazing idea, right? Because you can now link it together, right? You can link it together, turning it into a linked list. But they said pre-order traversal, which seems wiser in the sense that you visit your node, then you visit the left, then you visit the right, which is actually a good idea, especially if you are keeping track of. But in a linked list, they didn't mention that it matters. If you want to keep track of how the order is specifically, like, because in some trees specifically, the right is greater than the left, and as you go down, it becomes more and more. So especially if you want to keep track of how large it is. But in this approach, we're just using the pre-order traversal. That's what I said. That's the naive approach. So that's the brute force. And the right pointer of the dequeued node is set to the previous dequeued node. So it's similar to what I thought of, just the traversal method. This approach would require extra memory because it's a queue. So queues are O of n. However, it can be solved without any additional data structures. Can it be? Can it not be? So let's look at the optimized approach. So to flatten the binary tree, we'll follow a depth first search approach. So we start at the root node, and for each node, we're going to find the rightmost node in the subtree. So we set the right pointer. Okay. What I'm going to do, I'm going to play the graphic so we can watch it together, and then I'll read the question so that we can understand it better. Now, so let's see. So we go down. Okay, so it goes to the left first. Then it sets the pointer of this to the right child of the current. Okay, so you see how it's moving. It's showing us how it's going until we are straightened out. Okay, so just by looking at that graphic, I have a vivid understanding of how it's meant to work. So what I'm going to do now, I'm going to read the question, I'm going to read the solution again, because at first the solution was like seeming a bit blurry and foggy in my mind, but now I get it. So let's see. So to flatten the binary tree, we'll follow a depth first search approach. So we start at the root node, and for each node, we're going to find the leftmost node in the left subtree. So for each node that we have here, we're going to find the rightmost node. Sorry, we're going to find the rightmost node, because remember we said that we don't want anything to be attached to the left subtree, and then we're going to set the pointer of the rightmost node to the current node's right pointer, which was what we did. If you look at it here, right? So we started at the root node, which is 1. And for each node, we're going to find the rightmost node in the subtree. So we went to 2. Then the rightmost node here is meant to be 4, but let's see what they say. Okay, so they are moving this one to the rightmost node. So we'll set the rightmost pointer to the current node. So that we set the current node's right pointer to the current node's left pointer. So it moved from, it was at 1 before. Let's see what we had before. So before we had like 2. This is the left, right. So we use pre-order traversal. So we go to the left. Then what did it do? It then attached all the values to 2, right? All the values from the other side, from the rightmost side to 2. Then it then brought it back. Then we have 3 here. It attaches all the values, all the children. Let me not say all the values. All the children of the rightmost node to 3. Then all the children is also attached again. So it still keeps on doing this thing. And so you can even do this recursively. That's one thing I've learned about depth first search. Like a lot of times it has a lot to do with recursion. So it's good to have a solid background in recursion when working on these. So we set the right child of the current equal to the left child of the current, and so it's flattened. And another thing you can do, you can also play this from scratch as reading it. So you can just leave it as a loop as it's going. So I think I understand what it's doing. I hope you understand what it's doing, because it's basically just flattening it out. Looking at the code too would also help. Then we can now recreate it ourselves. So let's look at the step-by-step approach. So starting from the tree's roots, we traverse the tree in a depth first search manner. At each node, we check if it has a left child. If it does, follow a path down to the rightmost node of the left subtree. And this can be achieved by repeatedly moving to the right node. Wait, let's read it slowly. So starting from the tree's node, we traverse the tree in depth first manner. In each node, we check if it has a left child. If it does, we follow a path down to the rightmost node of the left subtree. This can be achieved by repeatedly moving to the right child of each node. Okay, so I'm moving to the right child of each node until we reach a node that does not have a right child. So right here we say if not root, we have a base case. Remember, always have a base case. So we have a base case here, which is saying if we do not have a root value, then just return. We do not, basically, we can't really flatten anything. Then it's saying then we're going to assign currents to roots. Okay, that's understandable. We want to assign it to something else. So I'm going to say while current. So while we have current, while there's a roots, it's basically displaying this. So this section actually is not very straightforward for me, confusing me. So I just go over to the solution and I read it and I understand what it's doing. Okay, and you also have like a solution summary part here. So it says if not roots, just return. So we can't actually solve anything. We can't solve anything. Then when we have the root, we're going to assign that value to current. So we're going to be saying while current, right, while we have a root value, we're going to say if current dot left. So if we have a left node, remember, remember in remember in a tree we have a left node and we have a right node. So if we have a left node, we're going to be assigning that value to last. So if current dot left, we're going to assign it to last. Then while last dot right, so when we have a right value, we're now going to be assigning last to last dot right. So that's going to keep happening as long as we have a right value attached to last. Okay, so last dot right is equal to current dot right is equal to current dot left, and then current dot left is equal to none. Okay, so this section, it can be very, very confusing if you are not drawing it. That's why I always like using this approach of looking at the values itself, right? One thing I'm going to do to seal up this knowledge is to solve this again, right? Just like math, without looking at this solution. But I just wanted us to have a firm understanding of how to solve it before getting into things directly. Okay, so current dot right, and then we return our root value. So, and also the solution summary is here, and the time complexity too for this is O of n, where n is the number of nodes in the tree, and the space complexity is O of 1. So it's a constant space that we are using here. And one thing you can also try to do, because one thing that has been happening to me is I'll be stuck when it's time to implement the code. That happened to me previously. So one thing I've been doing to improve on that is to actually use the solution summary, because I have an understanding of how to solve it. Use the solution summary to then code it out without looking at the code. This will help you to think and to grasp the concepts perfectly. Also, drawing it out would help. So this is the first day of study sessions with Mo. Thank you so much for coming, everyone that stopped by. I really appreciate you all. I'm sending smiley faces and heart emojis. So yeah, follow me on YouTube, by the way. Thank you. Have a good day.